Hello, in this video we're looking at related rate problems. These are worded problems, so naturally they pose challenges because you have to interpret what the question wants. So I want to start with breaking this down a bit by giving you what a related rate problem is before we delve into the worded problem. It's just an application of the chain rule. If you know the chain rule, you can do related rate problems. So I'm going to put a note over here of the chain rule, so we remember it. So the chain rule says that dy dx equals dy du times du dx. So the logic with the chain rule is that these two cancel, like they cross cancel, and you're left with dy on dx, which is the answer here. That's what these questions are asking. I have two questions here. They're taken right out of the book. They're asking you to use this formula. The challenge is getting each of these, finding out what the question wants. Once you've got each of these, it's smooth sailing from there. So let's have a look at problem 4 here. We have a spherical balloon being deflated and its radius is decreasing at this rate. As soon as you see a rate, underline it, make a mental note. It's very important. Anywhere where they mention a rate, put it on your page. So we have a constant rate of 5 centimeters a minute. We have to write it in the language of calculus. We have to take this and write it in calculus. Let's see. Well, the radius is changing. So we have dr. The d, think of it as kind of like the Greek letter, think of delta. The Greek letter delta, for you physics people, is used to say change. So think of d as change when you're looking at this. We're kind of saying the change in r with respect to the change in t. dr dt. The change in the radius with respect to the change in time. Let's have a look here. So we've interpreted this part. It's the change in radius with respect to time. Now here are some other tricky worded bits. Constant means that we're just going to have a number here. It's a constant rate, so it means that we're just going to have a constant number here, and it's 5. However, it's decreasing at a constant rate. So there's another tricky one again. If it was increasing, it would be positive, but it's decreasing, so it's negative. So this part here is saying dr dt equals -5. So we've already found one part of our formula here. Let's see, what's it looking for? At what rate is its volume decreasing when the radius is 4 centimeters? So it wants to know the rate at which volume is changing. So it wants to know how the volume is changing, or dV, with respect to time. So we don't know this. We know this. Now here's the thing. We need to use the chain rule formula to relate these rates. In other words, we need to use the chain rule to figure out this. Well, let's see. We've got dV dt, and looking at the chain rule, well, this is going to have to be on the other side. So we've got dr dt. What do we have to multiply by to turn dr dt into dv dt? Well, we don't want this dr business up here, so we'll need to have a dr down here to cancel it. So that would get rid of the dr, leaving a dt on the bottom, but we want a dv on the top. So let's put that here. Well, we know we want to find this. We know what this is, that's -5. dv dr, the change in volume with respect to the change in radius. How are we going to get that? How are we going to find dv dr? Looking here, I can't see anything that says the volume is changing by such and such with respect to the change in radius. I can't see anything obvious there. However, it is giving us a hint. It's saying it's spherical. So here's where you need to know your volume formulas or your measurement formulas. So sphere, its volume is given by 4/3 pi r cubed. Well, I've got v in terms of r, but I want dv dr. What can we do here? Well, we can take the derivative. We can take the derivative of v with respect to r. Well, let's bring the power down, subtract 1 from the power. We get 4 pi r squared. There we go. That's looking good. We've got dv dr. We've got dr dt. Let's sub these into our chain rule formula. dr dt is -5. dv dr is 4 pi r squared. Well, that equals -20 pi r squared. So now we have an expression that tells us the change in volume with respect to the change in time. And it's asking us the rate at which its volume is decreasing when the radius is 4 centimeters. So we have the rate that its volume is decreasing, it's -20 pi r squared, but we want to know when r is 4 centimeters. So let's let r equal 4 centimeters and sub it into here. dv dt equals -20 pi 4 squared. 4 squared is 16 times 20 is 320. What are our units here? Well, that's -320 pi centimeters cubed per, with respect to time, per minute. So that's our answer. The volume is decreasing at a rate of -320 pi centimeters cubed per minute when the radius is 4 centimeters. So here it's important to note we've decided to define the negative sign to be decreasing. So if we were to answer this as a sentence, we might say something like dv dt is decreasing by 320 pi centimeters cubed per minute when r equals 4 centimeters. So notice that by answering a worded problem with a worded answer, we avoid any ambiguity, we avoid anything that's unclear. Because the question is, at what rate is its volume decreasing when the radius of the balloon is 4 centimeters? dv dt is decreasing by 320 pi centimeters cubed per minute when r equals 4. We're saying exactly what the question wants. So we've kind of changed that negative into a decreasing. I think that's an important thing to note with worded problems. Make sure you grab that question and just rephrase it with the answer, just to make sure you are showing your examiner you know exactly what you're doing. Not much difficult computation there, but it's a new concept, so let's do another example. We have a bowl that's being filled with water at a rate of 12 centimeters cubed per second. Well, that means dV, change in volume with respect to time, is 12 centimeters cubed per second. Notice how I'm keeping it positive here because it's being filled. I'm defining that as a positive thing. The volume, oh, they've given you a formula this time, so that's quite nice. They've given you a formula to find how much water there is in the bowl based on the height. So we have V equals 8h to the power of 5 on 2. Find the rate at which the depth of water in the... Whoops, I've cut off half the question. Find the rate at which the depth of water in the bowl is increasing when the depth is 9 centimeters. So you can see I've cut off... Let's see if I can copy that in. No, let's just grab it. Find the rate at which the depth of water in the bowl is increasing when the depth is 9 centimeters. Bowl is increasing. Bowl is increasing when the depth is 9 centimeters. Sorry about that. So we want to find the depth, how the depth changes. Oh no, how the depth of the water in the bowl is increasing. What is this looking for? Find the rate at which the depth of the water in the bowl is increasing when the depth is 9 centimeters. Well, it wants to know the change in depth, which is h, so dh, with respect to time. So we've got dv dt, we've got this formula, we want the change in depth with respect to time. Let's use our chain rule formula. Well, we've got dv dt. Let's see, what's the other thing we'll need? Well, we'll need to get rid of that dv there. So let's do it that way. And we'll want a dh on top. This is going to get very interesting. So let's clear this, let's make some room. This is going to get very interesting. So we have this formula here. Well, it seems natural to take the derivative, so let's do that. dv dh equals, let's bring the power down. 5/8 are 40, on 2 is 20. Subtract 1 from the power, leaves you with 3 on 2. Okay, well that's all well and good, but it wants dh dv. We've looked at our chain rule formula. We need the change in height with respect to the change in volume. We've got the change in volume with respect to the change in height. So we need to take the reciprocal. You can do this. You can flip both sides. So let's flip this side and let's flip that side. Now we're looking much nicer. We have dv dt, which is this 12 centimeters cubed per second. We have dh dv. Now we can solve for this. So dh dt equals 12 times 1 on 20h to the power of 3 on 2. Let's tidy that up. 12 on 20h to the power of 3 on 2. We can simplify a bit there. That would leave 6 on 10, which is 3 on 5. 3 on 5 h to the power of 3 on 2. So we've got an expression for the rate at which the depth of the water in the bowl, dH, is increasing when the depth is h centimeters. So let's solve it for when h is 9 centimeters. Let h equal 9 centimeters. So that means dH dt equals 3 on 5, 9 to the power of 3 on 2. Okay. Now, 9 to the power of the half here. I'm going to do this a longer way to make it very clear. I don't want to skip this. This is quite tricky. 9 square root of 9. So the half part becomes a square root, and you're left with a cubed. So see how I've taken the half out of there and left the cubed? That lets us evaluate it. Square root of 9 is 3. 3 cubed is 27. 27 times 5 is 135. So we get 3 on 135. Let's see, does 3 go into 135? Yes, it does. How many times does it go in there? 4 3s are 12. 5 3s are 15. So that answer is 1 on 45. And that's depth with respect to time. So that's centimeters, and our unit of time is seconds. But just to be sure, let's answer as a sentence. We've been given a worded problem, and we want to make sure we answer the question. So let's say the rate dH dt is increasing by 1 on 45 centimeters per second when the depth is 9 centimeters. Good to have a sentence there. Alright, so for this exercise, I've asked you to do pretty much all the questions, and the reason is with a bit of practice, it becomes pretty automatic. So there are lots of dv, dh's, dt, dh's, dt, dx, and it doesn't make much sense until you practice it a few times. Once you do it a few times, you'll be totally on top of it. They're pretty typical exam problems as well, so it's good to get a lot of practice with these. I hope you found this application of the chain rule to related rate problems video useful, and if you have been, thank you for watching.